John Dalton was an English chemist, metallurgist and physicist whose revolutionary work into the development of modern atomic theory provided scientists with new ways of seeing the physical world. His efforts gave us our first understanding of the atom, bringing it from an abstract philosophical concept from ancient Greece to a concrete reality. Democritus first suggested the existence of the atom, but it took almost 2 millennia before the atom was placed in solid foothold as fundamental chemical object by John Dalton. It was in 1803 that John Dalton noted that carbon and oxygen could combine to make a compound, and whatever the weight of carbon, there was exactly twice as much oxygen. Dalton hence formulated his theory. The main principle of his theory was that atoms of different elements could be distinguished by differences in their weight. This theory proposed a number of basic ideas. All matter is composed of atoms. Atoms cannot be made or destroyed. All atoms of the same element are identical. Different elements have different types of atoms. Chemical reactions occur when atoms are rearranged. Compounds are formed from atoms of the constituent elements. Atomic theory allowed Dmitri Mendeleev to produce a periodic table of elements. This was a tabular display of chemical elements organized by selected properties of their atomic structures. This table is also very important in its role of providing the means for discovering new elements. His fundamental breakthrough of science didn't go unnoticed. Dalton's atomic theory began to receive much publicity and debate. Not everyone was convinced straight away. It took as long as 50 years to die down.
In 1897, Thomson suggested that the fundamental unit was over 1,000 times smaller than an atom. He discovered this through experimenting with cathode rays, which were deflected by a negatively charged electrostatic force. This was due to the fact that the cathode rays were composed of very light negatively charged particles. They were named corpuscles, which are now known as electrons. Thomson initially believed that the electrons emerged from the atoms of the trace gas inside his cathode ray tube, concluding that atoms are divisible. To explain an atom's overall neutral charge, Thomson created the plum pudding model, which was comprised of negatively charged electrons in a state of positive charge, just like plums that are embedded in a plum pudding. However, the electrons which were represented by the plums were rapidly orbiting, not stationary. Thomson also discovered isotopes and mass spectrometry. In 1912, Thomson and his assistant channeled a stream of ionized neon through a magnetic and an electric field, then measured its deflection by placing a photographic plate in its path. Two patches of light could be seen on the photographic plate, suggesting two different atomic masses for neon, which are neon-20 and neon-22. This was the first evidence for isotopes of a stable element. In conclusion, Thomson discovered electrons as negatively charged cathode rays were deflected by a negative electrostatic force. He then created the plum pudding model to represent this idea. The plums represented electrons which were rapidly orbiting in a sea of positive charge, which is the pudding. This was later proved incorrect. Thomson also discovered isotopes, as he found out that neon could have an atomic mass of 20 or 22.
From New Zealand, Ernest Rutherford became known as the father of nuclear physics. In 1907, he moved to England to become a professor of physics at the University of Manchester. Here he made a number of contributions to science. Working closely with his students, they were also able to make significant discoveries after his death. In his early work, Rutherford discovered the concept of radioactive half-life and also named alpha and beta radiation. The most significant discovery from Rutherford was his atomic theory, which I will speak about in more detail later on. He also discovered the proton and suggested the idea of the neutron, which one of his students discovered later on.
Which one?
The plum pudding model of an atom that J.J. Thomson found didn't really allow physicists to know how particles were distributed in an atom. There was no real evidence for it. Rutherford experimented with a thin beam of alpha particles and gold foil. He fired these beams of alpha particles at a thin sheet of gold foil and detected them coming out. He predicted that they would pass straight back out of the foil, but some would also be slightly deflected by passing electrons. Although many beams were deflected, some were deflected by a larger amount than expected. This shocked Rutherford, and he said it was like firing a 15-inch shell at a piece of tissue paper and having it bounce back. He decided that the only way this could happen was if all the positive charge was concentrated in the centre of the atom in one small place, with negative electrons orbiting the nucleus. This was like planets orbiting the Sun. Although slight adjustments were made to his model of the atomic structure, Ernest Rutherford's theory was widely accepted by most scientists. He gained many honours. This included the Nobel Prize for Chemistry. He was knighted, and the ultimate honour is being buried in Westminster Abbey.
Before Mosley, the atomic number was thought of as a semi-arbitrary ordering number which increased with atomic weight. In 1914, Mosley found the relationship between an element's X-ray wavelength and its atomic number. Mosley came up with the idea of a positively charged nucleus surrounded by negatively charged electrons, and the atomic number to be exactly the same as the number of positive charges, now known as protons. He did this after research for just 40 weeks at Manchester University. Mosley proved the theory of Maldives, Mayer and others wrong, that the weight was not the significant player in the periodic law. Mosley used the discovery of isotopes of the element to prove the properties of elements varied periodically with the atomic number. After being killed in World War I, just weeks after his findings, Mosley provided a chemistry breakthrough resulting in atoms as we know them today. His theory must have been accepted by other scientists because it's formed the periodic table that we use now.